Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to talk about the C++17 STDVisit function and how it is used. STDVisit. As we begin our conversation, we want to start by talking about callbacks and how they are used in something like an algorithm. This review will be relevant to understanding how STDVisit works. Initially, STDVisit might sound like a function which is a callback for STDVariant. As we will see, STDVisit is actually a way to examine the alternatives of a given STDVariant. A few examples will be provided in this video to show some interesting things you can do with STDVisit.
The definition of a callback in computer science terms is simply a block of executable code which is passed as an argument to another piece of code in your program. This will be implemented in different ways depending upon your programming language and what tools that language provides. For example, in C, callbacks are implemented by passing a function pointer to some other function. The callback function is passed as a parameter and will then be invoked at the discretion of the other function whenever it is needed. In C++, there is more flexibility due to additional options. The callback can be passed as a function pointer, a function object which can contain state, or a lambda expression. Although the data type of the function pointer might be known, it is worth mentioning that the data type of a lambda expression is unnamed, and will be different depending upon the compiler. So now we have a dilemma. How does the receiving function specify the data type of the callback? This is why the function which receives the callback must be implemented as a templated function or some other mechanism which can resolve the callback data type. This is an example of how a callback is specified with an algorithm. The stdCountIf algorithm expects a callback to be supplied, which will return a Boolean value when invoked. This algorithm will automatically invoke the callback for each element in the given range, and count the number of times the callback returns true. On the first line, we're declaring a vector of integers. Then we define a function called myCallback, which is responsible for checking if its passed parameter is greater than 5. Of course, your callback could do anything as long as it returns true or false. In both line A and B, the first and second parameters passed to the algorithm indicate the beginning and end of the data in our container we want to test. In the code for line A, the third parameter is the address of our callback function. Notice that there is nothing special about the callback function itself. It's an ordinary function that accepts an int and returns a bool. Any free function with a compatible signature could have been used here. For line B, instead of passing a free function for the callback, a lambda expression is used, and all the relevant code is located in the body of the lambda. For small callbacks, this can enhance readability and is often more convenient.
The templated class STDVariant is basically a container, somewhat similar to the vector in the prior example. Algorithms in C++ expect all of the elements to be the same data type, so they cannot be used with an STDVariant. If you are unfamiliar with the precise details of STDVariant, or you would like a review, you may want to watch the video we created, which goes into more detail about variants. So it would make sense for the language to provide a nice way to access a variant, and then do something with the data it contains. This is the purpose of the STDVisit function. In each variant, there are a number of alternatives, and usually each one is a different data type. When you call STDVisit, it retrieves the current alternative and then passes it to a visitor function. As part of using STDVisit, your visitor implementation must ensure the data type of every possible alternative based on the given variant is supported. Thankfully, it's a compiler error if you get this one wrong. Since the visitor code must be capable of receiving multiple different data types, a normal function or callback would not work. The visitor is often implemented as a generic lambda expression. It can also be a function object, where the function call operator is either templated or overloaded. In this video, our examples will use a generic lambda expression because we believe it is the most readable. In this code, we start by declaring a simple variant and then show two examples of how to assign a value to the variant and then call a print function. Our print function receives one parameter, which is the variant data. You could have defined the variant with a using statement, so the data type in the parameter list could be simplified for readability. Either way works just fine. In the body of print is where we make the call to STDVisit. The first parameter to STDVisit is a generic lambda expression, and the second parameter is the variant, which was received in the variable result. Since a variant can have only one value at a time, the value in the variant is called the current alternative, and it will be passed as the variable arg in the lambda expression. We need to declare arg as auto because there is no way to know what data type result will contain. For line A, the variant will contain the string ginger, and the call to visit will pass this string to the lambda expression. The variable arg will contain the string, and cout will print the string. The visitor lambda expression only needs to work for the data types listed in the variant, which are bool, int, and std string. For line B, the variant now contains the integer value 108. So visit will pass this integer value to the lambda expression, and cout will print 108. What is interesting to observe is our print function would not be easy to implement using printf. The printf function requires a format string, which would have to be different for each data type in the variant.
As we mentioned, the lambda expression parameter list must be declared with a data type of auto. So what happens if we need to know the data type? Is there a way to query for this? Well, we can. However, it is a bit tricky. You need to use a decal type expression to find the data type of the current alternative in the variant. However, all we normally need is the basic data type. The way you do this is by using the type trait stddk_t, which removes const, volatile, and references. This type trait will remove all the information we do not care about and leave us with the base data type. In the first example, when we apply the decay trait to the data type L-value reference to int, the data type t it returns is simply int. In the second example, the const is removed, and in example 3, the r-value reference is removed. Now that we know the base t, it can be leveraged in the visitor function. In this example of a visitor, we are only interested in the data type of our argument. We start by declaring a data member in our widget class, which is a variant. The first alternative in this variant is stdmonostate, which indicates an empty value. It could also contain a bool or an int. In the current type method, we want to know the data type of the current alternative stored in mdata. This is where we make use of the decay type trait to retrieve the base data type of the current alternative. Then we use the C++17 if constexpr functionality along with the std_is_same type trait to find out which of the alternatives we are currently looking at. Based on the t, we return the corresponding enumeration value. If the type t does not match any of our expected data types, we fail with a static assert. This means the code is safe, since it will not compile if we add a new data type to our variant and forget to include a new if in the body of the lambda expression. As another notation, you can produce the same result we achieved using a lambda expression by implementing a function object visitor with an overloaded function call operator. However, the latter code can be more complex to implement and less clear to read and debug.
In our prior example, the data type of the parameter in the lambda expression was const auto reference, which is usually what you want. The visitor is simply observing the data type or value of the current alternative, and then you do something. In this example, we have a generic lambda expression, which receives its parameter by L-value reference. This means the lambda can modify the value it has passed, and therefore change the value of the current alternative in the variant. Oddly, this is perfectly legal code. The effect of the double function is to add the current alternative to itself, which will alter the value in the variant. If the current alternative is an int or a long, this would result in multiplying the value by 2. If the current alternative is a string, the string will be concatenated with itself. The use of a visitor to modify the data in the variant might not be the best practice, since the visitor now has a side effect. On the other hand, this could be a very useful trick for manipulating the variant when nothing else seems to be a better choice. We do recommend that you declare your generic lambda expressions carefully and always receive the argument by const reference unless you actually intend to modify the variant data within the body of the visitor lambda.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.